Yeah, thank you very much. Titus would be doing. I'm noticing a problem here. Okay, it's playing automatically. So I'm Jonathan Snively, and I'm going to be introducing the Grand Challenges session on gravity wave coupling across scales and systems. And you might have seen that Titus Yuan has organized this session. I will note that all of the session details, were heavily developed by him, and I'm pleased to conform to that as I give this talk. One of the things that I'd like to acknowledge is that in this presentation, I'd like to provide the background of what is going to be covered in this session, where we're coming from, what we're interested in, what is likely to come next. And this is not by any means all-inclusive. So I'm going to be citing a lot of literature, doing a bit of a review, showing some things for context, example simulations, et cetera. But there's more to it, and I hope that this can be inclusive and not a compartmentalized effort on what is really a big and interdisciplinary set of problems. I think that's one of the dangers you have when you look at something from a Grand Challenges perspective, where you have so many moving parts and so many potential interactions within the community to really make scientific progress on it. It's important that we recognize that we don't just have the folks who are presenting this time, we'll have the folks who will be presenting next time and in the third meeting. So this is the beginning of a development there from session to session. So looking at, okay. So looking at the purpose of this, we're trying to identify and ultimately address the gaps and challenges in the area of ITM gravity waves. And ITM in this case refers to ionosphere-thermosphere, mesosphere, looking at waves that are coming from below primarily in this context. So the interest of this group then is to develop a coordinated approach to solving problems that can leverage multiple data sets, multiple perspectives, multiple models, recognizing that this isn't just something that folks do in a vacuum. So looking at the title here, there's two features of it that I want to clarify, because we're hearing more and more about this in sort of the common language of our community. One, we have things that are across scales, and this refers to processes that may be multi-scale in nature, but not necessarily multi-system. For example, when you have waves that are small, but ultimately have large impacts, small-scale waves that produce secondary waves that are of potentially much larger scale than the wavelengths of the original parent wave. These are cases where you can have an impact that conveys into a large-scale environment, or would impact a large model, but would not necessarily be represented in all typical simulations or contexts or all data sets, just due to the size of the volume. You also have the problem of across systems. And when I say across systems, I mean between the atmosphere and ionosphere, or between the neutral atmosphere and the associated chemistries that are interacting between these. Basically, if you have to describe it with multiple models, or you need to describe it with multiple systems of equations, this is one aspect of across systems. There's more to that too, in that you can also have the consideration of how you're actually measuring something, the observing systems that are defining a measurement of waves in some context or some process. You can include that as part of the system. So, for example, many of the measurements we derive in the ionosphere are captured via some radio means. And as a result, if you have an interest in understanding how radio waves propagate for the purpose of conducting a measurement, that ends up being part of the system, i.e. the basic equations of electromagnetic propagation and how you describe it. So in terms of the observable ITM region, the classical approach that our community would have taken, and when I say our, I mean the ITM minus the I community, the neutral, aeronomy, mesosphere, and lower thermosphere community would take, we would measure the constituents of the mesopause region and above to the extent that we can, and we would derive parameters of that state, the dynamics within, basically how they're perturbed, et cetera. And this is just scratching the surface, because again, at higher altitudes, you have the ionosphere. So looking at the observable, what I'm going to call the lower ITM, or the mesosphere and lower thermosphere, we have, for example, the transition to atomic oxygen that leads to lots of chemistries, and in particular, the airflow emissions that we can measure waves from. And as well, you have the metal layers deposited through meteors that are measurable via active means, for example, LiDAR remote sensing and profiling of this region to derive temperatures, densities, winds, et cetera, from those constituents. Now, in addition to that, because you have atomic oxygen at higher altitudes, you have reactions. You're going to have production of ozone that leads to reactions with hydrogen that produce the hydroxyl Meinel bands that are readily observable from ground or from space, and the shortwave infrared especially. Those are among the brightest features. The pink here represents the product of ozone and hydrogen, and in the model, these are actually, this is not just a graphic. This is actually part of a numerical simulation that's shown here in the visuals. The pink represents the shortwave infrared hydroxyl, but it really is a product of hydrogen and ozone that you see. The yellow represents, or gold represents, the sodium. The green represents the atomic oxygen. And you can kind of picture these layered here in the narrow region from 80 to 100 kilometers. Now, this is, again, just scratching the surface, because when we think about the rest of the ITM, you have the ionosphere, and you're going to have additional emissions and chemistries throughout this region of interest that you can measure. But in this talk, I'm going to focus on the fact that you have effectively the ionized medium that's going to affect radio wave propagation and thus lead to the detectability of perturbations within based on the properties of those signals. So when you get above the atomic oxygen emission, you obviously are having this transition into an atomic oxygen atmosphere. You have additional reactions thereof, and you have, as a result, ionospheric emissions, including UV and the familiar 630 nanometer red oxygen air flow emission that you can clearly see in imagery and even color photographs. And these also provide insight into the fluctuations of this region, of course. But again, the radio propagation is one of the cheaper ways to remotely sense the sort of middle ITM or lower bottom side ionosphere, and you're going to have signals that are basically modulated in different ways depending on their frequency. And you will see throughout our session, for example, that folks are sensing different parts of the lower ITM and middle ITM using radio means in the D region, ENF regions, and especially using trans-ionospheric propagation of GNSS signals to diagnose the vertical total electron content, as discussed in Shenrong's talk previously. So this is the basic observational stage that I wanted to set for this grand challenge, because the fluctuations within all of these systems are measurable, and you see perturbations then in your data set when you project it on a map, or you look at a time series, you see oscillations. And some of these oscillations are consistent with what we would refer to as gravity waves and acoustic waves, and in a spectrum, I'm going to call them acoustic gravity waves at the short period range. The reason I've selected the acoustic gravity wave spectrum here is because it kind of addresses two birds with one stone. And when you have a deep stratified atmosphere that's also compressible, you can have wave motions that exhibit both buoyant and compressible character. In other words, you're going to be moving things up and down. You're also going to be compressing, so you can measure both vorticity and divergence of your flow fields. So at the longer period range for acoustic waves, effectively the shorter than 3.5 minutes, you're going to have some role for the fact that there is a force of gravity as well. As the scales of these acoustic waves become large, they become large relative to stratification. They eventually approach a cutoff frequency. And in the lower atmosphere, 3.5 minutes, if you're talking about waves that are propagating from below, 3.5 minutes is your acoustic cutoff. That period is much longer, actually, in the thermosphere, where you have a much higher speed of sound. You as well have gravity waves with periods typically longer than 5 minutes in the lower atmosphere, and generally starting around 8 or 10 minutes in the lower thermosphere. Now, these waves, again, are the short period part of the gravity wave range. You're going to have other motions and modes that can establish themselves within this atmosphere. For example, you can have guided and trapped gravity waves, or acoustic waves, or oscillations that are bound by the shape of the atmosphere. You also have sort of nominal acoustic gravity waves that exhibit properties of both. And I like to call this the acoustic gravity wave spectrum because waves exhibit different properties at different altitudes. You can picture, you have a dispersion relation, you can define it at any altitude, and that changes dramatically with altitude. As well, I don't want to forget that gravity waves include those at larger scales, extending to those for which rotation matters. There's also the inertial gravity wave spectrum, and all of these are going to be interacting extensively with tides and planetary waves and other large scales. In terms of gravity waves that are propagating at, so your familiar small scale gravity waves, the direction of propagation relative to the vertical is going to be a function of frequency. So those that are higher frequency propagate more vertically, those that are lower frequency propagate more horizontally. And that becomes even more the case as you approach effectively an inertial limit. So this is, again, a quick review of the kinds of nomenclature that you would see in a session like this, where you're concerned with waves that are penetrating deeply into the atmosphere, so that will reach up well into the middle thermosphere. So I'm going to show an example here. This graphic is part of a numerical simulation, and this is, again, kind of an idealized test case just for the purpose of showing how the different waves disperse, how they evolve, and what they do. This is generated by a several kilometer scale vertical force applied at r equals 0. This is an axisymmetric slice, which is to say if you look down on this, you would see a concentric wave, but this is symmetric. There's no winds, it's just the wave itself. The time scale of this has a full width half maximum of just 2.35 minutes. It's a vertical puff, and then the atmosphere responds, and you have waves accordingly. The spectrum of acoustic gravity waves is generated with periods extending to basically 10-ish tens of minutes. But this is, again, a short period spectrum, so it fits well in this graphic. And the colored layers are the simulations of the species. The visualization is a little funny here. You're going to notice, do you see these are color-coded sort of gray regions? The blue are basically moving mostly downward. The red are mostly moving upward. And the gray haze is defined by the Mach number locally. So we can see it for waves that aren't necessarily just propagating vertically. So it's a color-coded description of the motion. The Mach number for these ranges from very, very small to 0.4, which seems pretty big. That's because gravity waves grow to fairly large amplitudes. And I'm going to just take a step to a later caption here. I had a nice video, and I can't display it because I had some technical difficulties. These waves have amplitudes on the order of nearly 100 meters per second in the vertical and horizontal, because they include waves that have frequencies close to n over root 2. When you look at stuff like this in a plot, you see this curvature of the fronts here. You see how you have basically waves that are more horizontal and waves that are more vertical. And then you have this stuff. This is basically two branches of the spectrum. We've excited acoustic waves, which are those that are propagating upward and outward in this sort of top of, oh, wow. I didn't even know that was possible. Who's that guy? And then you also have the gravity waves extending outward, and you have this degree of continuity of phase because, again, this is a spectrum of acoustic and gravity waves in one place. Now, do you see these sort of ridges here in your layers? When we look at layers of the atmosphere, basically, if you're looking at air glow, you're going to see fluctuations due to the waves. You're going to be able to use those as a diagnostic of the wave. You're going to see the atmosphere moving up and down, modulating how those layers respond. Especially if those layers are the result of chemical reactions between other layers that may have different peak heights and scale heights. So when we look at this wave field here, you can see that the amplitude has grown quite large. And the color coding here, this nearly saturated yellowy color here is corresponding to probably over 100 meters per second in the vertical at this boundary. But I want to make a point about altitude. Again, that's like 200-kilometer altitude. This is well into the thermosphere, okay, and well into the ionosphere. And we have to kind of get comfortable with the fact that wave amplitudes are pretty large up here because the speed of sound is really pretty high too. Speed of sound in this atmosphere is, many hundreds of meters per second. So looking at this wave field here, you can see again, you have lower frequency waves more inclined, you have higher frequency waves, then you have these acoustic waves, which have long periods relative to acoustic waves. We can wait, and these waves will eventually break. Now, this is, again, just a really idealized example. This is actually one of the test codes I use to make sure my code is running fast enough. It runs in a few minutes on a laptop. And what you see here is you have the onset of breaking. The waves start to overturn. But I want to look at the altitude here. this green here is the peak of the atomic oxygen layer around 96 kilometers. Above this is where most of this action is happening. Now, in reality, this is way worse because this is 3D, and you have other flows. You have the tides, you have planetary waves, you have pre-existing gravity waves. You may have hundreds of meters per second, literally flows that the wave has to contend with. In other words, something this dramatic might happen along one azimuth. You may have effectively a wave excite things concentrically. You may have some part of the spectrum you'll see emerge as this beautiful concentric field, but other parts you'll see the wave will dissipate at some altitudes, and the slower parts may effectively be removed completely. So as this wave field breaks down further, you're going to see secondary waves. Those are these features here emanating from the sides, and you're going to start to see interference of waves on this side. And you're also going to see, if you were looking at the video, you'd see little puffs here of acoustic waves passing upward further into the ionosphere. So as this wave packet dissipates, again, I want to make this point. Look at this. You have these really nice clear fluctuations in the layered structure of the mesopause. You have this picture of the waves as they're passing through that layer. But one of the caveats is you're missing this really cool region where they're all breaking up here, or if you had tides, you had other winds, the waves would be dissipating in different, more complicated ways. So identifying the sort of secondary waves that emerge from this, I'm just making a point about secondary waves. This is only one facet of this, because as we said, with the perspective of cross or multi-scale coupling, you can have waves that are small, that have big impacts. This is a small domain. If you evolve a breaking wave field in a large domain, you will start to see much larger gravity waves emerging from that. These waves here are basically interacting with themselves at r equals 0 in this axisymmetric domain. So you're going to see these sort of large-scale fluctuations in the center that are consistent with secondary waves that are kind of focused in the middle, but in reality that wouldn't happen. You just have radiation of different waves backward. You'll notice in the literature there's two bodies of work here. There's Sharon Vadis's work over the last 20 years or so discussing the net impacts of secondary waves that are generated through the dissipation of gravity wave packets. And this especially pertains to the waves that will be very large in scale and will fill large volumes and propagate near globally. There's also the waves that are reaching smaller scales. So we're going to see, when you look at the kinds of examples in models and simulations and in data, you sometimes see a reduction in scale, or you see similar size wave scales that emerge from the environment as other waves dissipate. So these are often through nonlinear interactions where you're going to have some information about that original spectrum preserved, and you'll see secondary waves that are maybe, for example, harmonics or subharmonics of a parent wave, or maybe you'll have evolutions of primary waves that have effectively interacted with the background, modulated themselves, shifted themselves to higher frequencies, and they'll penetrate to higher altitudes. That's called self-acceleration, and you'll see works by Fritz and Dong et al. On that. Now again, this review I've kind of selected to discuss the things that are the content of the first GC session. There's more to say. There's a lot more that's being done, and I don't want this to just be focused on the specifics now. I want us to be thinking about what comes next. There's opportunities then, of course, to leverage mesopause measurements to understand ITM dynamics. One example of that is if we look forward to the NASA AW mission, you'll have a perspective on the mesopause quantitatively in terms of the waves that are passing through that layer and specifics, the hydroxyl ergo layer. And that will sort of provide you this entryway door perspective as to what reaches higher altitudes. This is an opportunity then to understand what goes into what provides potentially the seeding for other ionospheric processes or other waves. And these kinds of observables are effectively neutral. I mean, even though they coincide with the altitudes of the D region, most of these don't depend strongly on the state of the ionosphere there. Now, this is a cartoon. I just want to note that this is not a simulated layer here. Matt Zettergren will talk more in the session about how these kinds of models couple together. This background wave here is just a quick demo in MAGIC. He'll be sharing the Gemini ionospheric model and how it couples with MAGIC using some new things we've been tinkering with called figments. And the opportunity next is, okay, you have this whole ionized conducting region of the atmosphere that is going to be modulating the propagation of radio waves. This provides another remote sensing opportunity that we can readily take to understand the waves happening within. So if you're doing even optical diagnostics for this region, there's going to be some dependency both on the neutrals and the ionospheric state. As well, if you're interested in the propagation of radio waves, the propagation of, for example, GNSS satellite signals to a receiver, you want to map those fluctuations, that's an opportunity to, for example, capture exactly these kind of waves. These are, tens of kilometer scale waves, the same kind of thing that'll show up in a high resolution processing of the GNSS total electron content when mapped. At lower altitudes, though, in the E region, you have lots of fluctuations. And this is, again, relatively untapped opportunity to diagnose the neutral dynamics. So that's a shock, seeing the white here. That hurt my eyes. This is, in summary, mesopause measurements capture the inputs to the ionosphere, but then these ionospheric measurements also capture a perspective on the neutral dynamics of the thermosphere, and that's a big opportunity. As well, just to understand the effects of the neutrals on the ionospheric state from the perspective of operations. It's also a measurement and diagnostics opportunity. And I'd like to see these kinds of sessions develop a sort of shared community dialogue about the value of this region for both purposes. I think that this was highlighted especially 10 years ago. A lot has happened in 10 years. And in particular, this paper, Nishioka et al. 2013, I think was one of the first that really made an impact on showing that the waves generated by severe weather, for example, penetrate into the ionosphere, carry very clear, specific concentric forms of the gravity wave field. Even in the ionospheric data, you're able to measure this part of the spectrum that is preserved probably at 200 to 300 kilometer altitude to some extent. As well, this pointed out that acoustic waves are really pretty important above severe weather. We now know from GNSS data that you see acoustic oscillations all the time. You find these 1 to 4 minute oscillations above severe weather, above natural hazard sources, et cetera. It was measured for hours. That's what these little lines are here to the south of the source. If you look at the time evolution, you look at basically the latitudes, equatorward of the more EF5 tornado and convective storm, you see these oscillations, and these are acoustic waves generated by the storm. So you have a strong vertical transient fluctuation at the bottom of the atmosphere. Now, what was realized very quickly is that this is just one layered perspective, so then you have to take a multi-layer perspective. You have to look at what else is in between to begin to use this kind of information to piece together the puzzle of what does the atmosphere look like when disturbed by a certain kind of source and gravity wave field, an acoustic wave field, et cetera. So multi-layer optical data sets at the same time provide a really big opportunity because you're basically taking a picture, you already have it mapped in space, you can see where the waves are, there are asymmetries with azimuth about the source, and you can make comparisons then with GNSS data. This is from a paper by Miller et al. I think if I click to the next one, you can see the underlying storm. This is from the SWOMI day-night band imagery. Irfan Azim, a few years later, shared the GNSS processing for this event, and this is the concentric wave field that is measured in the ionosphere, thermosphere above this effective mesospheric. This is likely, for example, the summed emissions of hydroxyl that fall within the camera's bandpass. So you're measuring an 85 kilometer perspective on the wave field, and here is probably a 250 to 300 kilometer perspective. You get a bias towards the bottom of the ionosphere, and that's really cool. Now, convective storms don't have a monopoly on perturbing the ITM, and we've realized also that mountain waves can be really strong too and really disruptive. This is something that we're just getting into from the perspective of potential impacts on the ionosphere, which in many cases will be secondary rather than primary, because the mountain wave field is nearly stationary. You have penetration into the mesosphere and lower thermosphere, but you do not have necessarily a spectrum of transient waves that propagate that well to higher altitudes, but you do have all of the transients associated with the breaking of the mountain wave to generate more waves that can be detected. This is from the Deep Wave, NSF Deep Wave campaign, organized by Dave Fritz. This is an instrument by Mike Taylor, the AMTM in the middle showing intensity. This was prepared by Dominique Potet, where you have the side cameras looking out from the aircraft. And this is basically flying over New Zealand. You can see here this wave fluctuation, and embedded within this, you see more small scale, I'm losing my little pointer, more small scale waves here, these around 20, 30, 40 kilometer scale. And one of the things that, of course, we were interested in doing was doing a model simulation of just a cross section of what this mountain wave might look like. This was Chris Heel's work here at the bottom. I don't know that this is working, but do you see the red line here tracking the phase fronts of the primary mountain wave and identifying the oscillations embedded within? What you have is a sort of a cascade from larger scale to smaller scale, and you establish the spectrum of mountain waves with embedded features. Now, we hadn't thought to look at the LiDAR data, which was also collected, and Katrina Bossert separately started working on a paper and identified that you see these really clear secondary features in the LiDAR pass through the atmosphere. So looking in sodium LiDAR, 70 to 92 kilometers, you see these small scale fluctuations, and you see spacing that is consistent with the scale of the wave. But in Chris's model simulation, we had not bothered to do this validation. So in talking to Katrina Bossert, Dr. Bossert, about this event, we looked at Chris Heel's model data and found that you have really the same scales appearing in this kind of very basic simulation. Captures just the initiation of the primary mountain wave of a specific character, but then it has the cascade, and the cascade process to all of these subsequent scales is clearly consistent with the data too. And that's a really neat finding with regards to the sort of predictability of relatively subtle features. This is not something that is visibly turbulent here, but you do have small scales that emerge. Other cases that are really compelling with regards to looking at multiple regions of the atmosphere at once, you're starting to appreciate that you can use AIRS data and capture some portion of the gravity wave spectrum that is going to reach to higher altitudes, as well as some portions that won't necessarily. And it's very nice having satellite imagery combined with really nice broad networked imagery from below. The United States has become an excellent laboratory for measurements, radio measurements from GNSS, and optical measurements, in this case, from the MANGO network. This is courtesy of Asibad, and I have a paper referenced here. Looking at the presence of multiple thunderstorms, you're going to have multiple wave fields radiated into the ITM, and this in particular is one of the clearest signatures I've seen at 630 nanometer airglow of gravity waves. You can clearly measure their scales. You can also take a look at the scales that are present in GNSS total electron content, which are similar. Using numerical simulations, you can then make comparisons. And one of the things that Chris Heel did was he simulated the effective latent heat release of the thunderstorm using the NextRad radar data to initialize a three-dimensional atmospheric model that spanned a large region. And I think a tiny bit of this will be discussed in other talks throughout the meeting. But what's interesting about this is when you do this, you have onsets of acoustic waves in the model and in reality that are really closely coincident. In other words, you have a measure of the transient timescales and evolutions that are embedded within the thunderstorm system, even though this is a very, very simple source. So we've been pleased to see that when you do this kind of simulation, you get very closely coincident acoustic waves between models and data. Now, looking in GNSS data, this is an absolute goldmine for assessing what makes it into the ionosphere, but it's looking at the top of the ionosphere. Again, you're missing parts of the bottom side. The E region isn't fully captured. We don't necessarily have a good grasp as to how deeply into the ionosphere you can project if you were to ever attempt tomography of this region. But when you look at what you can map from vertical total electron content, you get very high resolution pictures now of relatively small scale gravity waves. You see features like this pop up. You see the acoustic wave fields. This is filtered. These are acoustic waves over a storm. You see gravity waves of unknown mechanism, but there's a huge polar vortex distortion at the time of this particular event, and you see these really clear wave structures. You also see kind of routine, familiar traveling ionospheric disturbances. This sort of pattern here, as you would expect, not necessarily associated with gravity waves, but you also see sort of larger scale TID features reaching into mid-latitudes from high latitudes. Now, this is interesting because this really stands out. These kinds of events are relatively rare in terms of day-to-day, in terms of this coherence. Paul can correct me, but it is definitely an indicator of stuff that happens at high latitudes and works its way down to mid-latitudes, LSTIDs and TADs. But here's the thing that is interesting to me. We have a perspective on the waves that are generated by high latitude magnetospheric forcing and inputs. But the perspective then on all the other complications at high latitudes, the other dynamics there that can generate waves, that I think is just solidifying now. We do see waves, for example, this is a recent paper by Katrina Bossert et al. Published in 2022 using GUVI data, finding this really clear wave oscillation extending downward in latitude from the polar region. Now, this was taken during a time of quote unquote moderate geomagnetic disturbance, but with a major sudden stratospheric warming. A question is, can you see features of both in these data? Do you see evidence of waves that are emanating from the polar regions that are due to the specific meteorology of the stratosphere and upper troposphere? That's a neat question. Are we seeing evidence sometimes of different kinds of forcing mechanisms that are present there? Because we often do see waves coming from the poles. Not all of them correlate clearly with the timing of geomagnetic disturbances. Some do. This has certainly the possibility, but there's other cases that make you wonder. Other questions. When you're looking at the evolutions of waves at high latitudes, again, you get to low latitudes, you typically latch on to the very specific processes of convection and mountain wave forcing, but you have other distortions of the polar vortex that can radiate waves. Sharon Vadas has been working with Eric Becker on modeling of the evolutions of the vortex, as well as in synergy with other wave generation processes that are present there, for example, mountain waves. And at high latitudes, you see waves that may be due to both, okay? You have the forcing of waves from below from flow over mountains, but there's also a very strong reason to believe that you would have forcing of waves by the evolution of the flows within the atmosphere as well. These don't necessarily reach high altitudes, but it is a reminder that more is happening in the atmosphere, including at high latitudes, that is neutral in nature, that may convey into higher altitudes. In other words, we should probably be aware of both from below and above in the context of analyses of data sets reaching to the poles too, not just mid and low latitudes. It just is way more interesting and complicated when you have to contend with both processes. So when we're looking at waves evolving to smaller scales, there was a mention before of secondary waves that can be at large scales and at scales comparable to the source. We also see different evolutions of waves that are upward propagating. There's papers recently by Heel et al. 2022 on gravity waves from basically a slice through a simple convective source. You have radiation of secondary waves backward, but you also have the transformation of primary waves forward as they're refracted by their effects on the atmosphere. This sort of scenario leads to waves penetrating deeply to high altitudes, but these waves aren't necessarily secondary in the traditional sense. They have simply evolved as primary waves that reach higher and higher. When you look in the backward direction, you then have interactions between waves that are primary and waves that are secondary, and that means it's kind of hard to say. If you're looking at a single snapshot in time and you have a wave field that's evolved for a while, it can be difficult to attribute primary or secondary status at different parts of the wave field. When you get to a time-dependent evolution of a convective plume in GNSS total electron content data, yeah, maybe you'll see mostly primary waves, but you might see secondary waves later too. And if you are trying to diagnose just a satellite overpass of the same event, you're going to have more questions. Another point, when we talk about self-acceleration and the effect of waves on a flow, this is an indication that the wave is impacting the background via transport, and as well this affects the layers of the atmosphere. For example, air layers and as well the ionosphere. So when we see nonlinear gravity waves propagating through the ionosphere, you see nonlinear modulations of the ionosphere too, as effectively it's being displaced, but then it's also being forced to react because you have motion of the ionosphere in the presence of the thermosphere where you have the oxygen peak. So basically moving the atmosphere or ionosphere or any species that is reacting around is going to lead to different features such as depletions or enhancements that may persist. And one example in the small scale context, this paper by Wenjun Dong investigates the dissipation of gravity waves in polar mesospheric cloud layers simulated, and this can lead to the formation of depletions where the wave has effectively dissipated and imposed transport. The nature of that then depends on the specific microphysics that are included. Other things, an elephant in the room with regards to observational data sets at the much larger scale, our community is developing a much greater appreciation for the potential value of science to natural hazard diagnostics and towards understanding the responses of the system to really significant, severe, hazardous transient impacts. Volcanic eruptions are one very clear example. I'm pleased to see that this is being discussed because you have clearly the radiation of a broad spectrum of waves. You have a plume which generates more waves, and the transience is really neat from the perspective of understanding how those waves propagate globally and evolve. And I was pleased to hear the discussion earlier today on this. Here's an example of an image, and this appeared in press releases shortly after the event. This is at Mauna Kea, just a color photograph. Do you see these lines here? These are the arriving likely acoustic gravity waves approximately close to a Lamb mode in terms of the speed that would have been accompanying the propagation of waves at lower altitudes. And you see sort of this packet of oscillations pass over. The video doesn't work. And this is timed with around 300 some meter per second propagation velocity. And you can see it passing over. Eventually, waves reach the US. And this is just one example from our group that combines also multiple data sets from collaborating groups, reinforcing the value and importance of collaboration in really understanding multi-layered data sets, mapped data sets, network data sets, et cetera. It's important to work with folks to get the subtleties of for example, there's a mango imagery from SRI, courtesy of Asti Bhatt, Jonathan Makela, and help from Brian Harding as well. And these kinds of data sets are, for the case of Hunga Tonga, revealing the passage of waves over the US simultaneous with the passage of waves in lower atmospheric data sets. For example, in the pressure sensor data, the propagation of waves measured by GOES, et cetera. So the timing of these waves and the scales are all right around 295 to 320 some meters per second. And they pass over the US. And I'm going to just page through this here. I'm sure that Paul Vincent will be pleased to tell more about this if you're curious about it. There's some really nice modeling papers now coming out that are addressing these short duration, short period, fast, but large global scale events. That's a new kind of challenge in our field, is addressing things that happen quickly, catastrophically, that have very high impact, but that require a global perspective to address. It again requires many scales. This is a paper by Hanli Liu et al. Assessing the generation of transient Lamb waves in WAC-MX and the effects on the ionosphere and how this manifests in different data sets. This is, again, scratching the surface at a really broad spectrum of waves. Looking at some of the longer period features that emerge by different mechanisms, secondary waves are likely to be generated by a plume of the scale of the Hunga Tonga volcano. This is a paper by Joe Huba et al. Using the high MCM simulations reported by Vadas et al. 2023, and interesting, these are really large amplitude gravity waves emanating from above the source, and you also have formation of plasma bubbles and other nonlinear impacts on the system as a result of this. These kinds of cases really represent significant advances in current states of progress that we've had in this ramp up from coupling from MLT to ITM. And I appreciate the use of the language ITM specifically because it reinforces that stuff that is in the upper mesosphere, mesopause region, lower thermosphere is also likely impacting the ionosphere at some relevant scales. GNSS data, map data has been exceptionally valuable. Data from spacecraft, data from network imagers, horizontally distributed perspectives on how these evolve. This is all pretty exciting to me. And as well, we're getting better and better at having models that actually capture the relevant physics, and my button isn't working, and how to interoperate them together to produce compelling simulations that capture the evolution of events that we can faithfully compare with data. That comparison with data is, again, one of the future steps that we really need to continue to progress towards, because the better we can do with regards to reconstructing an event, the better we can do with understanding it, and as well devising new means to collect and interpret data. And we're seeing now the multidisciplinary value of some of these. At the same time, we have this Grand Challenge session, and there's a lot more to say. Fortunately, a lot will be said by folks other than me. There's going to be a series of talks, and I'll show the schedule here, but I would encourage you to look at the website for this. Some of the year one questions, we're interested in how waves interact with a large-scale background, but at the same time, we are very pleased to evolve that session to reflect the specific contributions that we'll have as we engage in discussion and make progress on this. The schedules, which I won't read off here, we have a session Monday today, 13:30 to 15:30 after lunch, and tomorrow again, an additional session, 10 to noon. So I of course encourage attendance and discussion, and please, if you have an interest in getting involved and looking at the future sessions that are hopefully to emerge in years 2 and 3, please be in touch and be aware of the opportunity to contribute. I also am always worried in our field that we have lots of different groups that are all doing relevant stuff, and sometimes you end up with this really exciting and important overlap between different sections. I hope that we can all interact together and we don't get compartmentalized into individual rooms and then forget that there's a bunch of really relevant stuff when it comes to coupling. So let us please keep the discussions open. Looking at some themes that emerge, this is just my temperature check of the talks that have been given. I went through and I downloaded all your recent papers and just got excited about reading them the other day. So I think that there's a lot of interest in global scale models that resolve gravity waves for one, but there's also interest in small scale models that play better with others in terms of accepting data from large scale environments, providing paths to scalability to larger scales, and providing coupling across systems, atmosphere to ionosphere, potentially vice versa, and to observables. As well, I'm pleased to see that we're seeing simulations with better comparisons to data, high fidelity scenarios and comparisons that are really guided by building up a story that you can tell with a computer as well as with your data sets to maybe inspire additional places to look. There's machine learning applications are emerging in the field and in the specific talks. Folks are finding ways to use these to accelerate models as well as to accelerate analyses. I think there's a lot to do, especially with regards to the future of parameterizations, where you can ideally use models to train the replacements and not necessarily have to simulate some of the finest scales that emerged. So questions of high latitude evolutions, what is happening within the atmosphere, what is happening from above and from below. Understanding that, I think, is a whole set of nice unanswered questions, and I'm excited to see initial progress on that and actually a flurry of interest. So extending from low and mid latitude perspectives on ionospheric dynamics driven from below to high latitude perspectives on driven from below in concert with from above, this confluence of coupling is really cool. So finally, there's so many pending optical measurements and radio measurements and actually just ongoing measurements in both cases. Understanding these data sets and the opportunities to dig deeper into each other's data sets is exciting. and I look forward to what else is coming down the pipeline. There's also a minor point, alternative measurements. Sometimes you can find other ways to diagnose things. You see signals not just in, you see the fluctuations of the system by waves, not just in the radio signals and the optical measurements of constituents, but also in indirect features, such as the magnetic fields that are driven by the currents of the ionosphere and the motions of charged particles along field lines. These sorts of alternate measurements are interesting as well. You have opportunities to diagnose things directly via accelerometry and in satellite platform context. And as well, we've been grateful for lower boundary conditions by surface pressure as they correspond to the rest of a wave field. I'm going to stop here because I see I'm 2 minutes over time, which actually, it could have been worse. Thank you very much for listening. And I really encourage you to attend this session among certainly any others. So, thanks. Are you allowed to call?
Thank you. My name is Xinzhao Chu from University of Colorado Boulder. Chris know me. Yeah. Okay. So Chris, thank you for this very nice talk and summarize of many recent results. I just want to make one comment. Is you probably are not aware out of neon HIDAR results. Yeah. Not only the McMurdo HIDAR observations from Antarctica provided the first evidence of secondary wave generation, but also recent development, we are able to measure temperature in the mesosphere and the thermosphere at least 2.5 minutes resolution. So we were able to cover the full, complete gravity wave spectrum. When calculating sensible heat flux, sodium flux stuff. Then the third one I want to point out, you showed this coupling from near ground all the way to 300 kilometers. And the recent results, we worked with the Chinese HIDAR colleagues. By detecting calcium ion, Ca+, we were able to measure from about 80 kilometers all the way to 300 kilometers over Yanqing Station near Beijing. And you can see these lots of wave features. So I think for US community, it would be time to develop even more powerful calcium ion HIDAR. So we can combine with iron, sodium, these thermosphere, ionosphere metal layers. We can help to study these multi-scale waves across very high altitude range. Thank you.
Thank you. That's really, I really appreciate knowing that. I was not aware of the new calcium LIDAR results. So I'll be grateful for a reference for that. It sounds spectacular. I completely missed that, and I apologize. That sounds fantastic. And I've been looking at the development of LIDAR technology has been really exciting for effectively having a quantitative perspective on that vertical column. So yeah, thanks for mentioning that.
Thank you, Jonathan. I enjoyed your talk as much as she described. Let me ask you, how well do we understand the role of viscous dissipation in the thermosphere region? When you showed model plotting of gravity wave propagation in the thermosphere, you're making some sort of assumption regarding the importance of viscous dissipation.
Yeah.
Could you comment on that, please?
Yeah, so, well, for a lot of these waves, we do think that classical viscosity is going to be a dominant means to dissipate them, in addition to all of the nonlinear processes that cause cascades to smaller scales and make the viscosity more effective. So one of the things we've been doing is, from a model perspective, we've been trying to take steps towards better descriptions of that classical viscosity and as well the environments that lead to how waves evolve. One of our students and collaborator So Benedict Pinheiro and Roberto Sabatini have been testing a new formulation of our model, for example, that includes diffusion between species and has a more comprehensive description of bulk viscosity and modulations of the lower thermospheric viscous diffusion coefficients as waves evolve. So that's one thing that we've been taking steps towards, but then there's also the question, if you want to extend to higher altitudes, certainly you'll have to start looking at pushing things further away from the Navier-Stokes approximation. So for the scales we're looking at, I think we're well within Navier-Stokes, within the limits of tracking the species that you're modulating. I think there's a lot more that can be done, especially as you look beyond the thermosphere. So, yeah, thanks.